here to get the dot product and the denominator. is row 3 plus 3 of row 2 to get the 0 below there. So this becomes 0. This is still 1. This is 0. And 0, 0, 0. So this already row echelon form. So you could actually just do back substitution in this case from here. So each column corresponds to those K1, K2, K3. And you can see there is leading 1 for each of those. And so you can go from the below, like the lowest one, that's K3 equals 0. Then next row K2 equals 0 also. And from the first row, K1 equal to negative K2, but K2 is 0, so this is 0. So they're all zeros. We call this trivial solution. Like that's a unique solution in not infinitely many, but a unique solution in a homogeneous system. Therefore, linearly independent set. I'll say trivial solution only because infinitely many has trivial solution, but also has other solutions. Linearly independent set, okay? So that's what we got for this, part A. If we got missing leading 1, for example, like if it was one leading 1 was not there for one of those cases, that would be linearly dependent because according to definition, if not all k's are zeros, linearly dependent. Now, next question says, explain why this set does not form a basis. So it's not that the matrix is 0. So the linear combination is equal to a 0 vector, like a 0 matrix. But when you put it in augmented matrix, that those constants, so it's a homogeneous system. Those are zeros because of that 0 matrix. But you're looking for if you get all k's are zeros. So, or if you were using determinant, if determinant does not equal to 0, then it would be linearly independent because you're reducing a matrix and you're getting all leading coefficients, all leading ones, I should say. But if some leading ones are missing, the k's, then you introduce a parameter, you're saying k, let k3, for example, equal to t. And then you have infinitely many solutions, k's, and that makes it linearly dependent because not all k's are 0 anymore. Some of them could be something else. So why would this not form a basis? So look, take a look. It's still referring to the same question. So we have 3 matrices, linearly independent. Why doesn't this form a basis? Remember, for basis, we have to have 2 conditions satisfied. They have to be linearly independent. And another condition, what is that? They have to span. Now, do we have enough to span 2 by 2? How many do we need to span 2 by 2 matrices? 4, yes. So need 4 linearly independent matrices to span M 2 by 2. So therefore not a basis, since only have 3. Three will not span, need 4. Exactly for the, because if you think of even dimension of M 2 by 2, that's it's equal to 4. Now this question is not related to the one we just did, even though it says part C, but it's a separate question. Which of the following are bases of R3? So it's still talking about bases, but now it's R3. So you can see how the first one is not, because it has only two vectors. They won't span. Two will, there's not enough. Two will not span R3. What about two, double I, the second one? Will that form a basis? No, why not? There's four of them, so four, so this will not be either, because four will be automatically linearly dependent, right? Too many, right? Linearly dependent in R3. So next one, we have the right number, but we kind of, by observation, it's hard to tell. So this one, I would put it as columns as a determinant and check if it doesn't equal to 0, because if it's a basis, it has to be linearly independent, and then determinant should not be equal to 0. So if I use the last column, it's easier than not even to use a 3 by 3 trick, or you could still use 3 by 3 trick, but I find it's easy to use cofactor expansion because you have just one non-zero entry. So you go 8 multiplied by -1. I'm in row 2, column 3, so 2 plus 3. Cross out row and column where 8 is. I'm left with 1, -1, 2, 1. And I'm doing these multiplied together minus these. As long as I don't get 0, that's all I care, right? So this is 1 minus -2 is +3. So you can see this is not going to end up equal to 0. You can see how you end up with a -8. I'll maybe even say it's -24. So that does not equal to 0. So this would mean you have linearly independent. And you have 3 of them, so they will span. So this will be a basis. Technically, you should put them as columns. I mean, it won't make a difference because remember, determinant, when you transpose it, it will still be the same. So, but like if you were thinking of like linear combination, they become columns. But it would not make it won't change the conclusion. Now this next one is a little more tricky. So it looks like it's the same except this number is 6. So if you don't see by inspection, so if you check by inspection and think of this as vector u, this is vector v, and this is vector w. If you can try by inspection, see, can you get vector 0, 8, 6 using the other two? So maybe like multiply it. So, and it's not as easy to see, but I know somebody, even in the previous workshop, came up. Yeah, because if you do 2 times u plus v, you will end up getting this one. So you can do 2 times 1, 2, 2, plus 2 times -1, 2, 1, and you'll get w. So it's like saying 2u plus 2v equals w. But of course, you can also do the determinant if you didn't see this. So that means these are linearly dependent because you can get one of them written as a linear combination of the others. So it cannot be a basis. Yeah, so I see other people also noticed the adding them and multiplying by 2 gives you w. So yeah, so it won't be a basis for that reason. Now for question 5, the set S where those are V1, V2, V3, they tell you it is a basis of R3. So if I wanted to find a coordinate vector relative to this basis, this coordinate vector is basically made up of the coordinates k1, k2, k3, such that when you multiply those coordinates with the vectors from the bases, you get this vector v. So always read carefully what the question is asking. What I'm asking you here is a little more difficult, actually, because you have to solve the system of equations to find k1, k2, k3. If instead they gave you coordinates, like they gave you coordinate vector, and you had to find this vector v, that would be easier, because then you just put those numbers in, multiply, and add and get the other side. So always read carefully what they're asking you. For us, it's a little bit more work. You have to do the row reduction. There's no way about it, because like even just doing determinant is not going to help you here, because it just tells you if there is a solution, but you actually have to find the k1, k2, k3. Okay, so I know we already got some practice with the row reduction, so I'll leave this for you to do, to row reduce this matrix to find those. I'll just tell you what you'll get, and of course you can easily check your answer, because you should be able to put the numbers in and get 1 to 1 on the other side. Oops, there should be 1 to 1. So you can decide if you want to use row echelon form or reduced row echelon form. So either one will do. Okay. So for people who want some extra practice for row reducing, definitely give this a try. But for the sake of time, I'm going to tell you what you'll get. You'll get k1 equals to -2, k2 equal to 0, and k3 equal to 3. This is sometimes written like this vector v relative to this basis s, set s, as -2. So it's a vector. So even if it's with matrices, it still will be a coordinate vector, because you just put it as a vector like this, right? Okay, we have 3 minutes left, but I might stay a little bit longer to finish it off. We have a set of multiple choice questions, like multiple select. So there's more than one correct answer for these. So we're going to try that. So if you can stay a little bit longer, we'll spend a few more minutes. Of course, also come to Math Study Hall to ask any questions about these or anything that you came across as you study. Okay, so question A, which of the following statements are true? So there could be more than one true. Ben is going to be there. I'm doing online today from 4 till 5. So if you can join online, you can also do that from 4 to 5, but Ben is in person there. I think it's 12:30 till